Ladies and gentlemen, welcome to your next vodcast in our kinematics series. Today we're going to consider acceleration. And again, we're going to use an example you see here on the screen. You see an example of what I'm calling a sail car. And that sail car is moving to the west. Okay, we'll call left, west. And it's moving into a headwind. And over a period of time, that wind is going to cause the car to change its direction. So we eventually will get to solving the problem of this particular example, but first let's review some basics about acceleration. Remember that there are three ways to accelerate. Okay, we've got speeding up, slowing down, and this is the one that usually surprises students, changing direction. So these are three ways to accelerate. But that doesn't really give us the definition of acceleration. So let's look a little more closely at the definition for acceleration. It is, we'll start with the formal definition. I realize that this is not a very useful one, but it's eventually you'll want to be comfortable with this because this is the way that we have found is the most precise way to describe it. Okay, it's defined as the rate of change of velocity. Okay. And we can actually write that even in symbol form in the following way. Okay, and by symbol I mean equation form. So I'll come down here and actually write that in. It's a little hard to type the equation. So we write that this way. And that triangle is the delta for change, like this. Okay, so this statement, acceleration, is defined as the rate of change in velocity. The way that you turn that into an equation is just like this, right? This equation would be read in this way, okay? And these are three ways up here. These are three ways that we can change velocity: speeding up, slowing down, and changing direction. And again, to make this as concrete as possible, remember that we can relate this these three ways of accelerating to the motion of a car. Here you see a quick sketch. Either the speedometer is moving up, the needle's moving and increasing speed, right? Or we have slowing down, decreasing speed, or we could be moving at a constant speed, right? The speedometer is not moving at all, but the steering wheel is moving, okay? And really the way that you're going to make acceleration make more sense to you is to remember that acceleration is very closely linked to the unbalanced force on the object. So remember from Newton's second law, right, that the unbalanced force and the acceleration do the same things at the same time. So Newton's second law, right, F equals ma, and this is an unbalanced force. We put this symbol here in front of it, right? Unbalanced force and acceleration do the same things at the same time. So we can keep track of acceleration by keeping track of the unbalanced force. So definitely when we come back and work on this example, we're going to want to consider the free body diagram on this sail car so that we can look and see how the unbalanced force is, if there is any, and that will give us an idea of the acceleration. Okay, we've kind of covered some basics of acceleration. Now we'd like to come back to this example problem, and the goal of this problem is to find what the acceleration is of this sail car, okay, during the period of time that the wind is blowing on it. So what I'm going to do for you is I'm going to model for you a problem-solving approach that we're going to use all year long. Okay, and I've come up with an acronym for this approach, and the acronym, of course, is this SCLEPS up here. Okay, and each letter stands for a step in the process. So I'm going to model that for you, and we're going to go through each step and arrive at our solution for this problem. The first step, S, stands for sketch. So typically you will not be given a drawing like I've already given for you here. You'll be given a problem in words, sort of like I've written underneath. And your first goal is to take this word problem and put it into a picture. Okay, now a lot of students think that this is just busy work, but this is actually making your brain work, right? Making your brain picture what's going on, and that's a significant step. That's a significant part of problem solving in physics. Okay, the next step is called, I'm going to call it C for coordinate system. Okay, you need to set up a coordinate system. We've talked about this a little bit before. A coordinate system means define where the origin is and define which way is positive. So let's come over here on our sketch and let's do that. It makes sense. Again, remember, you the physicist get to pick the origin where you want to put it that's most convenient to you. So I think that the start point, right, where we first see this sail car, that's a good point to put the origin. And typically on a piece of paper, if we're moving in just one dimension, typically, and you can choose another way, but typically we choose to the right to be positive. Okay, so in this case, that's going to be east, right? To the east is positive. Okay. All right, so now in addition to the coordinate system step to defining the origin and which way is positive, we're going to add another part, okay, because we're practicing these motion graphs. So as part of the coordinate system step, I would like you to draw the motion graphs for whatever problem you're working on. In this case, we're going to have three graphs again, right? PT, VT, and AT. And we're going to draw the graphs for those and then move to the next step. So I'm going to pause and draw the axes, and we'll come back. And this will be a good time for you to predict what you think the motion graphs will look like for this particular problem. Okay, let's try this. If you think about it, I think you'll realize that this is another situation where we're going to have negative position because we're starting at the origin and we're going left. Okay. Now, if you consider the motion speeding up, slowing down, or keeping a constant speed, I think you'll see that this sail car is slowing down, right? So that means you're going to have some sort of curve. And the only question is there going to be a steepening curve or a flattening curve, right? And since we're slowing down, that tells you that it's a flattening curve. So I'm going to move in a negative position, okay, like that, something like that. Golly, it's hard to draw these. All right. And now somewhere over here, right, we're going to come to a momentary stop, and then the wind is going to push us the other way, right? And then we're going to start to speed up. So it's basically going to look like something like that. We're not going to quite get back to where we start, okay? And I'll talk a little bit later about why I know that. But basically we go in a negative direction, slowing down, momentary stop, and then speed up in a positive direction, okay? Now over here, that's going to look a little bit something like this. We're going to have a negative velocity. Okay, we're going to have a negative velocity, but we'll be slowing down. Now remember, this is what really throws students. You're actually going to have a rising line because remember the zero is right here in the middle. And then you're going to speed up in a positive direction. So yours is going to look something like that. Okay, the velocity time graph. This is slowing down in a negative direction, momentarily zero, and then speeding up in a positive direction. All right. And down here, this one's quite simple. Okay, we have a constant positive acceleration the whole time. Constant positive acceleration the whole time. And you might wonder where this comes from. This will come straight from the free body diagram. Okay, so we're going to go ahead and add a free body diagram as well, and then you'll see where this acceleration comes from. Okay, here you see the completed free body diagram. And you see that the free body diagram shows us that we have an unbalanced force on the sail car. Now in the vertical direction we're balanced, right? The normal force from the ground balances out the weight from the earth, the pull of the earth on the car. But in the left-right direction we have an unbalanced force to the right. And since we have an unbalanced force to the right, we're going to have an acceleration to the right. And since we've already defined to the right as positive, that makes a positive acceleration. Okay, so there you have it. That's why this one is positive. Now I'm not sure why it turned white on me, but you get the idea. All right, let's go back to our problem-solving approach. The next method is to list. Okay, the L is for list. And at this point you're going to list all of the variables, okay, that you have based on the coordinate system that you've set up. Okay, so we have a couple of things here. First of all, there's the initial position, DI. Okay, the initial position is 0. We started at the origin. Then you consider your final position. We don't know anything about where the car ends up. Now, I happen to know, just because of my previous knowledge, it's not going to quite get back to the origin. All right, now we know something about the initial velocity. Okay, it's actually a negative 6 meters per second because remember, now that you've set up your coordinate system, that 6 to the left is actually a negative. And then the final velocity, I believe it tells us, is 4 meters a second, and since it's going to the right, it's positive. Okay, we also don't know the acceleration. That's one of our unknowns. But we do know the time, which is 8 seconds. Okay, so this is an important step because this will begin to point you in the direction that you need to go for the right equation, right? You want to list the variables first, see what letters you have, what letters you need, and that'll tell you which equation to use. Now at this point we only have, obviously we're going to be using this equation today, so it's not a big deal, but in the future you're going to have a number of equations to choose from and you won't know which one it is unless you take a look at these variables. All right, let's go on to the next step, which is the E for equation. Okay, so the E is for equation. And like I said, we already know which one that is. So let's go ahead and write it. We'll go ahead and write it again, but we already know it in this case because there's only one. So this is the equation that I'm going to use to mathematically solve for the answer here. All right, next step is the P, and that's for plug in. Okay, in other words, you want to plug your numbers in. Okay, plug in numbers. And so that's the next step. And into the equation, we're going to plug our numbers. All right, so we're going to say A equals, and this is going to be, delta always stands for the final velocity, which in this case is 4, minus the initial velocity, which was -6. So watch how I do that. I keep track of my signs that way. Okay, final, I'm going to write that above here. Final minus initial. That's what the delta means, right? Final minus initial. And then underneath we have the 8 seconds. Okay, and then finally our last step, the S. Okay, come down here. The S stands for solve, which is, that's the math part, where you actually plug into the equation. Okay, so over here, 4 minus a -6 is actually 10. 10 over 8, this is meters per second. This is seconds. This comes out to, what is that? 5/4, 1.25. Now watch the units, meters per second per second. You actually have 2 seconds. 2 sets of seconds there to keep track of. So we can say that our final answer is as follows: 1.25 meters per second. That's how you say that. Okay, and we would have to say east, because acceleration also has magnitude, right? Magnitude here, the number, and direction. So because our answer was positive, right over here, our answer was positive. We know that the direction is to the east because in our coordinate system, positive was to the east. We can also write this as 1.25 meters per second squared. Okay, let's make some closing comments here. I've reproduced our example down here lower on the screen, and I want to make a point here about a common misconception in terms of vocabulary. I'll go ahead and type it out. Negative acceleration is not the same as deceleration. Okay, negative acceleration is not the same as deceleration. And I think often students come into a physics course using these words interchangeably. So let's look at this example here. Okay, if you look at the motion of the car, it's moving to the east, moving to the west, slowing down, right? That slowing down is called deceleration. Okay, so it decelerates to the west, comes to a stop, and then accelerates to the east. Okay, but the whole time it actually experienced a positive acceleration. Okay, so even when it was slowing down to your left, to the west, it was actually experiencing a positive acceleration. Why? Well, not because positive acceleration means speeding up, but because positive acceleration means a push to the right. And the whole time this car experiences a push to the right, therefore its acceleration is positive. But notice that doesn't mean that the whole time it was speeding up. Part of the time it was slowing down. Okay, so I kind of wrote the converse here. Negative acceleration is not the same as deceleration. I could also write positive acceleration does not always mean speeding up. Okay, positive acceleration does not always mean acceleration. So that's an important point to keep in mind. The final point I want to make is about the units. Okay, so if you come over here, meters per second or meters per second squared, we actually have, we can write acceleration in a variety of ways. Okay, I'm going to give you some different examples here to wrap up. We could have, for example, we could have 1.25 meters per second per hour, or 1.25 meters per second per minute. In other words, this is one of the few times in physics or science in general where it's okay to mix the units. Okay, we have two different time units here. And if you look at these three different types of accelerations, they all have the same number, but they mean means something very different when it comes to what the speedometer is doing. Okay, if you think about which one of these is the largest acceleration, okay, you'll see that there's one is clearly a much higher acceleration than another. In other words, in one of these, even though the number is the same, one of these, the speedometer will move a lot faster than the others. Okay, and that's this one here, because it tells you that every second your speed is changing by this amount, meters per second. Right? I'm going to write it like this: parentheses second. Right? Whereas this one here is just telling you that it takes a whole hour to add that much to your speed. Right? It takes a whole hour. It's supposed to be parentheses. And then finally, this one here is sort of in between. Right? It tells you that it takes you a whole minute to increase your speed by that amount. So even though all of these have the same number, because of their units, they have vastly different values of acceleration.